atoms. So actually it is atoms, both these together is a unit. Atoms and nuclei is a unit. So we will first start with the Thomson's model. First we will discuss what? In this chapter what we're going to do, we're going to first discuss the different type of models. Different models of atoms. How different models were used to come to today's picture. We will go from Thomson's model, then we will go to Rutherford's model. We will look into the Giger-Marsden experiment. You remember Giger-Marsden experiment, that gold foil experiment?
Yes,
from Giger-Marsden experiment, then we will go to Bohr's atomic model. So Bohr's, why Rutherford models was rejected, what are his limitations, okay? Then we will come to Bohr's atomic model. Then use the concept, use the principles of Bohr's atomic model on a hydrogen-like atom. And then we'll find out that in the hydrogen-like atom, that before we go to the hydrogen-like atom, we will understand different spectrums. What are spectrums? What are they actually? Okay? And how many type of spectrums are there? How can you, looking into spectrum, and you can say that, you can say many things about it. Okay? Then we'll come to hydrogen-like atom. We will study hydrogen. Then while dealing with hydrogen, we will get introduced to different spectral series. Understand? Different spectral series, and this is how we'll proceed. Okay. So now let's continue. So first of all, have you heard about what do you call Thomson's model?
Yes, sir.
So what is Thomson's model? Thomson model of an atom. Thomson's model of an atom. Although this is a complete failure, Thomson's model of an atom. This is the beginning. This is the first beginning of Thomson's model of an atom. What is it?
Thomson's
model of an atom. The Thomson's model of atom is based on plum cake model. I'm not going to do much here. In this, he believed that the atom is like a cake, which is filled with positive, is completely positive, and electrons are plugged in, are plucked like plums. Okay, like this. This is the picture of plum cake model. In short, we're not going to go in deep because this is the first one who tried to explain how does an atom look like. But then this theory is a complete failure. It could not explain complete failure in the sense. How is the failure? It cannot explain these spectral series, spectral lines, different spectral series of hydrogen. It cannot explain spectral series of hydrogen. It cannot explain, or different spectral lines it cannot explain. Then it cannot explain that all this thing, whatever we will learn next, everything he won't be able to explain. Okay, what is excitation? How can you get electrons get excited? Atoms get excited. Can't explain. So this theory is a complete. Its thing was a complete failure. Complete failure. However, it do laid a foundation to investigate more on what is actual picture of an atom. That means what is macroscopic in the microscope, because we cannot see an atom, na? So how does it look like? So then comes the famous experiment. Before we go to Rutherford atomic model, next comes the Rutherford atomic model. Rutherford's atomic model. In Rutherford atomic model, before we can proceed deep into it, we need to look into the Giger-Marsden experiment. So what was Giger-Marsden experiment? This one I have discussed with you in the beginning.
Yes, sir.
Giger-Marsden experiment. What is Giger-Marsden experiment? Yes. So yeah, tell.
So there, a small light is, or any ray is passed through a small hole that is on a screen, and we will see the dispersion of those rays, and when it hits the surface of the other surface, then
what are you saying? No, this is the alpha particle scattering by gold foil.
uh,
That is Giger-Marsden experiment, na?
yes, sir.
So Giger-Marsden experiment we had a, so this is the gold foil. From here the alpha particles is coming from a radioactive source. It hits it, and after that what happened? It gets deflected in different direction. This is one, like this it get deflected. How it is getting deflected? Some of them even retrace its path backward. So this is our alpha particle. So this is the thing. And now more properly, there is a screen placed in its surrounding. There is a screen which has been kept in its, is here like this. So let me draw properly. This is a screen. So let me place a, in the form of a, in this form it has been placed. The function of the screen, it is just a photographic plate. When alpha particle hits this screen, it creates scintillation dots, because alpha particle has a property of that it affects the photographic plate. So when reach this photographic plate, it gives rise to a scintillation dots like this. Okay, or else how are we going to understand that there is alpha particle has went through the photographic plate? How can we say that? So this is the gold foil, Ag, very thin gold foil. This is the alpha particle coming from a, there is a lead box here. There is a lead box in which the alpha particle has been kept. Okay, from a radioactive source, alpha particles are being collected. Okay, and then it falls on this. This is the Giger-Marsden experiment. It was observed that what is happening is that these alpha particles which is coming towards, projected towards the nucleus, some of the alpha particles is being positively charged. So alpha particle is actually what? Alpha particle is, if you know, how do you write it? Alpha particle 4He2. 4He2, that is the number of protons in this is how much? 2. Okay, so what is happening in nucleus? So some of the alpha particle which is coming straight, they undergo a head-on collision. This is the, up to this much it can penetrate, and then it retraces path backward. However, those are not targeted towards the nucleus. They will move away from here. Understand? So this distance we can easily find called the impact parameter. We can use it by something called impact parameter. So based on this distance, if this is 0, it is a head-on collision. This distance is called impact parameter. Now this was observed. So the conclusions to this experiment, so Giger-Marsden experiment. So Giger-Marsden experiment, what are the observations of Giger-Marsden experiment? So Giger-Marsden experiment was carried out. Giger-Marsden experiment was carried out. So it consists of what? An alpha particle, highly energetic, and highly energetic alpha particle. Energetic alpha particle is incident on a gold foil. The gold foil. Okay, so is incident on a gold foil of then it is a screen is placed around it. which is nothing but a photographic plate, which is a photographic plate, okay, understand?
Yes, sir.
And then so it is observed that alpha particles get scattered, that alpha particles get scattered in all direction, okay, and when they hit the screen, and when these particles hits the screen, hit the screen, I mean by photographic plate, okay, hit the plate, it creates,
Hits the plate.
this is a photographic plate, it creates a scintillation dot, it creates small dots, okay. Okay, these dots when viewed, from these dots the scattering angle at which different alpha particle gets scattered is measured, and a graph is plotted, okay, graph between scattered is measured, just write measure, it will do, is measured, okay. So a typical graph showing the variation of number of alpha particles scattered to scattering angle versus scattering angle is something like this. So if you plot the graph, I will see something like this. So you see, this is the graph. You'll see there is, it decreases. So what do you see? This is number of particles, number of scattered particles, number of scattered particles to number of scattered particles to scattering angle. This is scattering angle, theta phi, whatever you want to do. This is n. So you can see.
So one number of scattered particles versus
scattering angle.
Okay.
So what do you see? At lower scattering angle, okay, from the graph it is clear. From the graph it is clear that at lower scattering angle number of scattered particles is more. You can write like this. From the graph, it is clear that the lower with the
At lower
increase. No, you can write
scattering
like low scattering angle. Yeah, the lower scattering angle. The number of scattered particle is particle is more.
more.
But how if when theta increases? But when theta increases, means scattering angle increases,
Theta.
number of particles, number of scattered particles is also less. Scattered particles is less. Number of scattered particles decreases. But when theta increases, that means scattering angle increases, then as the scattering, not when, but as theta increases. As theta increases, so number of scattered particles also decreases. Okay?
Number of scattered particles
As scattering angle increases, number of scattered particles also decreases. Okay? Okay, there are very few, we can see that there are few alpha particles which will get, there are few particles, there are few alpha particles which get scattered which get scattered at an angle greater than 90 degree, and even few retrace its path backward. May I clean the board now?
Yes, sir.
Based on these observations, Rutherford concluded. Based on these observations, Rutherford concluded. Please write, I am saying. Number one. Based on this observation, Rutherford concluded that there is a central core. The central core where the entire charge and mass. Central core where the entire charge and mass of the atom is concentrated.
Where the entire?
There is a central core where the entire charge and mass is concentrated. Is concentrated. He named this core as nucleus. He also found that electrons are observed. We also observe that electrons revolve around the nucleus. In circular orbits. In circular orbits. Okay? And then he found, next one, right? There is lots of empty space within the atom. This is lots of empty space within the atom. Empty space within this atom. Empty space. This, he said, because in Giger-Marsden experiment, this is based on the fact. No, not fact. This is based on the observation. Based on the observation from Giger-Marsden experiment, Marsden experiment, that few alpha particle penetrates the gold foil, that few alpha particle penetrates the gold foil, few alpha particle penetrates the gold foil
The gold foil?
without getting deflected. Without getting deflected. That means there is a lots of empty space, na?
So getting deflected, huh?
And then he said, next one, the atom as a whole is electrically neutral. The atom as a whole is electrically neutral. That is the sum of charges on electron and nucleus. The atom as a whole is electrically neutral.
Neutral.
That is sum of the charges on the nucleus and the electron is 0.
So, pardon, sir?
So sum of
That sum?
the sum of the charges on charge on the electron and the nucleus is 0. Okay?
Sum of the charges.
0. So this was your Rutherford atomic model. But Rutherford atomic model makes a tremendous mistake in this. Okay, there's a huge mistake in Rutherford's atomic model. So Rutherford atomic model, what is this saying? That we have seen that there is a Giger-Marsden experiment in which some of the alpha particles will go straight, some will get what 90 deflected by 180 degree deflection, some will get deflected by 90 degree, and some will get deflected by maybe little bit more, like this way. So based on these observations, as seen on the photographic plate, you can see the Giger-Marsden experiment, picture of the Giger-Marsden experiment. I just want to show you this is the picture, Giger-Marsden experiment. That is not interested. Look at this one. This is the actual one. Don't look at all those stuff. What Wiki has to say, let's see. This is the Giger-Marsden experiment. What is it? This is the Giger-Marsden experiment. Any other picture I have here? So you can see alpha, this is getting scattered. This is the scattering angle. Okay. Now here is this picture. So that is the gold foil from where alpha particle is the source, and you can see it's getting scattered in a different direction, right? So this was their experiment. So the Giger-Marsden experiment, also called the Rutherford gold foil experiment. Okay, but a landmark series of experiments. So you can see we have been able to now tell that there is some core which is called the nucleus. Understand? So this is the actual picture, actual setup, the one which you see in the book, and this is different. Here is the picture. This is the one. This is the main picture. You can see this is the 3D model of that picture. You see there is a gold foil. This is from where the alpha particles will be coming through, and you will hit it, and all around there is the photographic plates, so we can take the different from there. So as a result we will be able to see it. You see, this is how it rotates. Correct? This is in another view. Now then the best is this one, what they have built it, what they have made it. This is the one. Can you see? I think you can see now.
Yes.
Very small. Picture is very small. There is a gold foil. From here the alpha particle will come through this tube and will hit it, and then it will rotate. They have opened this section for you to see. And there is a plate over on all this side. So from there we will be able to calculate. Okay. So this is the Giger-Marsden experiment, and there you see they have also said this the plum pudding model. So this is the plum pudding model, Thomson's plum pudding model. This is what I was telling you. So it's a failure. Plum pudding model. So how come this is a plum pudding model, na? So how come alpha particle being charged? How come you say that the whole this plum cake model, the cake is positively charged, right? And these blue dots, they are negatively charged. So how come the alpha particle will pass through? If it is positively charged, it should repel. You have learned Coulomb's law of repulsion.
Yes, sir.
So then how can it pass through it? So it is wrong. So this is Rutherford model. Okay, so let us come back to now our work. So based on this he gave this, but there's a tremendous failure to Rutherford's atomic model. There's a huge failure to atomic model. So before we go to failure, disadvantage of Rutherford's model. So disadvantage of Rutherford atomic model. Let's see. Rutherford's atomic model. What are they? Now there is a classical electromagnetic wave theory. Classical electromagnetic wave theory. Okay. So please write. I am dictating. According to Rutherford model, and random model, the atom consists of a central core nucleus.
The
Atom consists of a central core called the nucleus. Core called the nucleus. Nucleus. And electron revolve around the nucleus in a circular orbit.
So an electron
revolve around the nucleus. Around the nucleus. No, don't write cycloid. Just write around the nucleus. So an electron while revolving. So an electron while revolving around the nucleus. The nucleus in a circular orbit may accelerate or decelerate. May accelerate or decelerate. May accelerate or decelerate. But then in classical electromagnetic wave theory, according to classical electromagnetic theory, wave theory,
but according to classical
electromagnetic wave theory, an accelerated charged particle emit radiation in the form of an electromagnetic wave, Okay, hence the energy of an accelerated electron, the energy of an accelerating electron should decrease accelerated electron should accelerating electron should what you call accelerating electron is a radiation in the form of electron. Yeah, should emit don't write decrease, should emit radiation and its path should be spiral rather than a circle. And with the emission of radiation, its energy should drop. Its energy should drop. An electron should follow. An electron should follow a spiral path before it eventually falls on the nucleus.
Falls
on the nucleus. Okay, so next, so you understood, so you should follow this path and follow on the nucleus, but this is not what is happening. Okay, now also next point, also the same theory, that means classical electromagnetic theory says the frequency of the electromagnetic wave, the frequency of the electromagnetic wave emitted by the revolving electron, the frequency of the wave emitted by the revolving electron depends is equal to the frequency of revolution of the electron. Okay, so next line. So as electron spirals inward, so as electron spiral inwards, so its velocity and frequency, changes continuously. Yeah. Hence, so the frequency of the electromagnetic wave emitted by the electron, so the frequency of the electromagnetic wave emitted by the electron should also change continuously. Change continuously. This means we should have a continuous spectrum. Okay, which is incorrect. Okay.
Yes, sir.
So what I have explained to you. So what Rutherford model says that, in simple what I am saying, Rutherford model says that we have a nucleus and the electrons revolve around the nucleus. So if it is moving in a circular orbit, so there is an electromagnetic wave theory. Electromagnetic wave theory says that Whenever electrons are accelerating, they will give out radiation. Okay, they will emit energy, whose energy is directly proportional to the frequency of the rotation of the electron. Correct? So, if it is accelerating, it should give out radiation. If the electron is not accelerating, no energy is being given. But if it is accelerating, let's say it is moving in a circular path. Okay? So, it is one kind of accelerated motion. So, when it is accelerating, then what will happen? It will give out radiation in the form of it will give out radiation in the form of electromagnetic wave. Correct? So, as it releases this, its speed should fall, its velocity should decrease. As its angular velocity decreases, it should move in a spiral path rather than moving in a circular path. And if it moves a spiral path inward, it should fall on the nucleus. So it is not possible. So how can, if the electron falls on the nucleus, so then everything, the whole universe should collapse. Because if atoms is not present, how do you think a molecule is present? If molecule is not present, how do you think an object will be present? And if an object is not present, how do you think the planet is present? And if the planet is not present, how do you think a solar system will exist? And how do you think a whole universe will exist? Right? So this is wrong. Secondly, again due to this theory, it is said that as this frequency of this wave which the electron is releasing, it is based on the rotation of this one. If it is moving in 2 Hertz, this frequency will also be 2 Hertz. Correct? That means when we see the spectrum, it should be a continuous spectrum. Now, what is spectrum? I will come to next. What is spectrum? Clear? So, spectrum is where we can see all the systematic arrangement of electromagnetic wave, one after the other. And how to see spectrum, I will explain it to you. So then, but in reality, we do not see a continuous spectrum. We see the spectrum has some lines, only certain lines. Either there is a dark background and a white lines, or there is a white background and some dark lines. So we'll see that now. What is this? So what is this spectrum and all? We'll learn now. So these are the 2 most important disadvantages of Rutherford atomic model. Correct? Now let us come to, before we proceed to the next, Bohr's atomic model, we need to understand something about the spectrum. What is the spectrum? Before we see the spectrum, let me explain you, there are 2 types of spectrums up there, which are mostly important. These are emission spectrum and emission spectrum and the absorption spectrum. So what is the emission spectrum? When a gas or a vapor is excited under low pressure. Under low pressure means, what do you mean by low pressure? By low pressure, we look at this container. This is a cylinder. Imagine your room. Clear? Now imagine the top floor of your floor. It can be brought down and up and down. Correct? So if this piston is gradually brought down, you have let's say 4 liter of gas. Correct? Here, 4 liter of gas presented. You are pushing it, you are compressing it, right? You brought the piston up to this much region. That means now it is under extreme pressure.
Yes, sir.
But if the piston is up, it is at low pressure. Means for 4 liter or let's say 2 liter, that is, there's a huge volume is there for you for small amount of gas. Then that means it is in a low pressure. Okay, not very high pressure. Pressure is not very high. Okay. So if when a atomic gas and a gas or vapor is excited under low pressure, low pressure, it is observed, low pressure, this is low pressure usually by, how do you when a gas or vapor is excited under low pressure, usually by,
So it is observed.
when a gas, no, wait, don't write that. When a gas or vapor is excited under low pressure, usually by electric discharge, then you write, it is observed that, it is observed
So 1 minute, under what?
under usually by electric discharge, under low pressure, usually by electric discharge, it is observed
Discharge.
the emitted radiations from the gas, the emitted radiation from the gas has a spectrum, which contains
Spectrum.
which contains
Which contains
only certain specific wavelength, certain specific wavelength. Okay, this kind of spectrum with bright lines on dark background, this kind of spectrum with some bright lines on dark background,
background
is called emission spectrum.
is called
Emission spectrum.
spectrum.
So can you see the picture here? This is the emission spectrum. Dark background, some bright lines. These are colors of light, different colors of light. Okay, it can be of different thing from the different electromagnetic spectrum wave. Okay, so this is the electromagnetic spectrum, this is the emission spectrum. So how do you find a spectrum? How do you see a spectrum? So you see, we have a prism, we use a spectrometer to do it. So we have a prism and this is a slit, correct? So the light which is coming from that gas, try to understand, the light which is coming from the gas, the room where we have placed the gas and we have discharged it, we have given some spark, correct? That light is passed through this slit, very thin slit. Okay? And then to make, the purpose of the slit is to make the light more of a beam. Okay? Now when it falls on the prism, what do you see? It should have been a 7 continuous color, but 7 continuous color is not there. Only certain colors is present. And there is a huge gap between. That means those colors which are in present between them, they have been absorbed or they have not been released. This is the concept of spectrum.
So it has not been released or absorbed.
That means this is not by released. No, you can just draw this spectrum. You can draw this picture here. I'll draw this picture. You see, so this is the prism here. This is the prism. Here is our slit. Our slit is present here. So the wave which is coming from, this is our slit. So the wave, radiation which is coming from here, it becomes a straight line. It becomes a straight line, falls on this and undergoes dispersion. Undergoes dispersion. Correct? It undergoes dispersion from here to here. And then from here, it gets splitted into different colors. So this is the one. Then from here, this is the one, and so on. Correct? and we get what? We get a spectrum here. This is nothing but, this is a photographic plate. This is a plate. We place a plate here. Okay? So in this photographic plate we will be able to see this. And even if you don't have photographic plate, if you have a simple spectrometer, you'll be able to see it. Okay? But for infrared and all, you cannot. For the special thing is required. So this is how we can say. That means, so if this is, let's say this is red color and this is blue color, we know for the VIBGYOR, VIBGYOR, we are getting blue and red. What about green, yellow and orange? What about indigo and violet? Where are they? So in the emission spectrum, they were not being emitted.
They have been absorbed.
They have been absorbed. Or now it is not necessary to do that. Okay? In some other cases, it may be for one particular gas only this thing has been emitted, and for some other gases maybe green and yellow only be going to be emitted, but that will not be. So this is the concept of spectrum, emission spectrum. Let us see now absorption spectrum. So when I look at this, I will see what? I will see a very dark background with some non-uniform lines. This is one line, this is the second line, this is the third line, maybe one more line here, and that's it. Maybe this is red, this is some other color, this is some other color, and gradually as it goes, it becomes faint and faint and faint. That means it is changing the spectrum. It is changing from one particular wave to getting into the other. For example, it is going from infrared to going into the visible, and from visible to is going into the another. It is like that. Okay. So let us come to the next one. That is the absorption spectrum. So absorption spectrum. So you write absorption spectrum. Absorption spectrum.
Yes.
When a white light is passes through a gas, the transmitted light when observed using a spectrometer found to have certain dark line, that is certain frequencies or wavelength are missing. Okay, so these dark lines corresponds to
Yes, sir.
those wavelengths which were found in the emission spectrum.
Spectrum.
Okay, so absorption spectrums are so these kind of spectrums with dark lines on white background.
So these
This kind of spectrums with dark lines on white background is called absorption spectrum. As you can see here, can you see these dark lines? Look at the picture, there are some dark lines. Okay, so you may draw this picture. I'll have a, so you don't know a spectrometer. What is a spectrometer? I can show you this. I have a hydrogen lamp in my physics lab. Okay, so this hydrogen lamp thing, when I put it, I also have a spectrometer there. I have a spectrometer there. So this hydrogen bulb, I'll show you in hydrogen lamp. I'll show you in hydrogen arc lamp. The one which is used in, this is the one. Look at this. I'm talking about this one. I'm talking about this one.
Okay.
This is the one. Okay? This is a lab called Incumens. When I use this is the spectrum. This is the one I make in our physics lab. So you need to have this, and you need to have a spectrometer. Yeah, this will do. What is it? No, not this one. This is the one. You can see there is a collimator here, there is a prism table here, and you see this is the one. There is a prism table, there is a collimator, and there is a telescope. So I will be placing here the hydrogen bulb. Dark room. I'll glow the hydrogen bulb. The light will go through this slit. Okay, and it will become this line. It will become like this, and as it becomes like this, then the prism is going to make it disperse. So when I see here through the telescope, what will I see? I will be able to see only certain colors, certain visible colors. I will be able to see red. Okay, I will be able to see this one. You see, I will be able to see this. Red is there. Now this is a very important picture. I'm coming back to this. This thing I do in BK Bajura Physics Lab. Very few people can comprehend this. You can see this. You see, this is the red one. This is the blue one. This is a violet. And you see, it becomes thin and thin and thin and thin.
Yes,
we will come to this thing. What are these red ones? What is this green one? What is this blue ones? I'm coming to that very soon. This is a real life experiment. This cannot be negotiated or cannot be replaced by the thing which is shown in the book. These actual life experiments. Okay, so this is a great article. This one I will keep it for my site. So now you can see, right? So this spectrum is this spectrometer. I can use this spectrometer, and when a student look through this one, they see the light is standing here. Light is standing there. All this light. They will see this. They will see what? They will see this picture.
These lines are formed inside the telescope.
Yeah, when looking at the interstellar in a dark room, you're going to see this. And I will tell you very soon. This is called the H alpha line. This one is called the H beta line, H gamma line, and so on. Okay? And these are different series. This is called the Balmer series. Balmer series in the visible region. So different time they have jumped from one orbit to the another, and as a result, what happened? They have released that particular wavelength. So you can see this. Do you see? Now next topic is, I'm going to say that Balmer series says that. So I hope your concept on this is clear. What are different emission spectrum and absorption spectrum? Without this you cannot proceed to the next topic.
Yes, sir.
So let us come to now. Let us come to spectral series. Come to spectral series. Spectral series. So you see, hydrogen is the simplest. Is right. Hydrogen is the simplest atom. Okay. The spectral lines of hydrogen the spectral lines of hydrogen is distributed irregularly.
Of spectral lines of
Distributed irregularly.
hydrogen.
Distributed irregularly. Distributed irregularly. Written?
Yes, sir.
That means, within bracket you write, spacing between spectral lines are non-uniform. Spacing between spectral lines are non-uniform. Spacing between the spectral lines are non-uniform. Are non-uniform. Okay? However, within a spectral however, within a spectral line,
Spectral line.
within spacing at the within a spectral, however, however, what did they say?
So, however, within a spectral line,
With the spectral line, certain set of lines are uniformly spaced. Certain set of lines are uniformly spaced. These are called spectral series. These are called spectral series. Come to the picture now. So what are these? All these red lights are.
series.
What are all these red lights are?
So which?
Look at the red. The red is the main line. And after that, there are thin intensities of equally spaced red lines or not. And again green.
Green, then this.
So these are different spectral series.
So these do not fall like the green as we can
Look
see.
at the red and blue, red and violet, red and blue. So different, blue and violet, non-uniform distribution. But within the red region, you can say like this, within one particular region of the electromagnetic wave, I can see within that particular wave there is a uniform spacing of lines. These uniform spacing of lines, what you call? They are called spectral series. They are called spectral series. Okay?
And so these are not, the green colors and the other colors are not visible because they do not fall under the...
No, you can see the green color. How can you say it's not visible?
So, I mean, it is not as visible as the other...
The intensity is getting fainted.
Uh-huh.
Red light being the longest wavelength, you can still see it. Green, violet, as you go from red towards violet, the intensity is getting fainted. Now you go even further. Let us continue. I will keep this picture and we will continue again and again. I will come back to this again. Okay? So you write. The first spectral series was observed by John Jacob Balmer. The first spectral series was observed by John Jacob Balmer. Balmer in the visible region. In the visible region of the hydrogen spectrum. In the visible region of the hydrogen spectrum. Hence on his name, it is called the Balmer series. Balmer series. It is called the Balmer series. So what can you see here? So this is, you are looking at the Balmer series. You are looking at the Balmer series. Balmer series. Correct?
Yes, sir.
He observed this. He was just he was a higher secondary teacher, physics teacher, who observed this thing. Okay.
Oh.
Then he was also carrying out some experimental demonstrations like this, and he came across this one.
Hmm.
The line with the longest wavelength, that is the red one,
Yes, sir.
is called the H alpha line.
The line.
With the longest wavelength is called the H alpha line. So you can see. So first of all, you classify this. Is it a absorption spectrum or is it a emission spectrum? Absorption or emission?
So, emission.
It is. You can consider this to be emission spectrum. Okay. So you can see, but this article is saying it was in the continuous spectrum. So what is continuous spectrum? Continuous spectrum is the one where everything is continuously the full given, right? So yeah, but you can see there are this is the emission spectrum. The one which you are discussing is the one is here emission spectrum. You can see, wow, look at this. This is sodium lamp.
Okay, sodium lamp.
Sodium lamp you can. This is another one. Neon lights.
Neon lights.
Contains lots of lines of red region of the spectrum. Correct? You can easily solve all. You can easily do this thing in lab. These things are easily available. Correct? So you just need to have that lamp, put it on the spectrometer, put it through a prism, send it to a prism, and check what happens. Correct?
Yes, sir.
So now, so then the line with the longest wavelength is called the H alpha line. That is the red one is called the alpha line, H alpha. We write this like this way, H alpha.
H alpha line.
Okay. The next line in the blue-green region, is called the H beta line.
Beta line.
And the next in the violet region is called the H gamma line, and so on. H gamma line, and so on. Okay?
H gamma line and
Okay? As the wavelength decreases, the spacing, the gap between the lines
lights.
become more and more close. Becomes more and more close. Becomes more and more close. And the intensity becomes more. And intensity also become more faint.
More faint. Huh?
Balmer gave a simple empirical formula. To calculate the. Balmer gave a simple empirical formula to calculate the wavelength corresponding to different lines. Okay.
Yes, sir.
Where I have written this, where R is called the Rydberg constant. Where R is called the Rydberg constant.
Huh?
Rydberg, RYD, Rydberg's constant.
R is called.
The Rydberg constant 10 to the power 7 per meter. So for H alpha, H beta, H gamma, I leave it for you to determine. For
Yes, sir.
for H alpha,
So
okay,
10 to the power 7 meter inverse, no?
7 meter inverse. So for H alpha, so wavelength corresponding to H alpha will be, you have to write this 1 by lambda would be equals to 1.08 into 10 to the power 7, then 1 by 2 square minus 3 square.
1.
So that gives me 1.08 into 10 to the power 7. So 1 by 4 minus 1 by 9. Correct? So how much is this? So 1 by 4. I'll use the calculator to solve it fast. So it should be
So for alpha, why did we take 3?
because the line will come to that. We'll come to that. Okay, it will get clear. It will get clear. In the next part of this chapter, it will get clear. Isn't it? Are you finding it interesting or not?
Yes, sir.
So it should be 0.15 into 10 to the power 7 1 by lambda. So lambda would be equals to lambda should be equals to 1 by 0.15 into 10 to the power 7. So that gives me 10 to the power minus 7, and 1 divided by, these are rough calculations, 6.66, and it is actually 6.95 most probably. It is H alpha line is how much? I think H alpha, is it clear all this thing?
Yes, sir.
H alpha line in hydrogen spectrum. So they are just 656 nanometer. Okay, so it is coming to, if you solve this, so approximately it will come to 650, no 656, mine is coming 666, is actually 656 into 10 to the power minus 9 meter, that is 656 nanometer. I leave this for you to find. Similarly, you find it for H beta. H beta would be 1 by 2, say everything being same, R 1 by lambda equals to R, it should be 1 by 2 square minus, now why is it always 2? We'll come to that, don't worry. 1 by 2 square, 1 by 4 square. Then H gamma would be 1 by lambda is equals to R 1 by 2 square minus 1 by 5 square, and so on. Alpha, beta, gamma, and then gamma done. So you do this too. How much is this, how much is that? Do it, because it comes. Calculate the H alpha, H beta, H gamma for the others. Okay?
Yes, sir.
Okay?
Yes, sir.
After this discovery, other spectral series of hydrogen were discovered. These are,
Should I write?
yeah, you're right. These are number 1, Lyman.
Sir, so if you could repeat.
After this discovery of after the discovery of Balmer series,
Palmer series?
other series
Where?
of the hydrogen spectrum is discovered. These are
Hydrogen
Lyman,
spectrum.
Paschen, Brackett, and Pfund. Pfund series.
Lyman, Bastian, brackets, and Pfund.
Yeah, so you remember Lyman series is this is actually n1 square minus n whatever you give, n square. This is Lyman. Balmer is we will do this. I think I will take one more class. 50% is done. More than 50% is this chapter is done. Okay, this is R. R 1 by 2 square minus 1 by n square. Balmer, Lyman, Balmer, Bastian. So you can see, if you understand, it's a very excellent chapter, no?
So this is with 3
square. So now you can calculate it. You can see that which one is what. Bracket. The rest part is still left. It will be even more interesting. 1 4 square by 1 by n square, and then finally Pfund. Pfund will be 1 by lambda equals to R 1 by 5 square minus 1 by n square, and so on. Okay?
Yes, sir.
Okay, then I'll keep it up to this far. Understand?
Okay, sir. Yes, sir.
So next class, one more class I will take to finish this one. So only the Bohr's atomic model is left, and 1 or 2 numericals.
Okay, sir.
Okay then.
Yes, sir. Thank you, sir.